So, okay. So thank you very much for the invitation. Today I'm going to talk about the asymptotic symmetries at the spatial infinity. The idea of this talk is to give a very brief introduction of this topic of asymptotic symmetry at the spatial infinity. I will start with some introduction, which is, well, we all know that the BMS group was shown long ago to be the group of asymptotic symmetry of gravity in asymptotically flat spacetime. This group naturally emerged at the spatial infinity. However, analysis at spatial infinity did not exhibit any sign of BMS group. This was shown in the paper by Regetelkenboom a long time ago. Interestingly, this discrepancy was recently resolved by Margenot and Cedric-Trossat by considering appropriate parity twisted boundary conditions at the spatial infinity, leading to a full agreement with the result at non-infinity. So as I mentioned a couple of seconds ago, the idea of this talk is to give a brief introduction on this topic on infinite dimensional BMS group at the spatial infinity. I will start with the case of electromagnetism, which is the simplest case. And then I will move and briefly discuss the case of general relativity. The idea is to provide some ideas or provide some context in order to give some context for some subsequent talk, which will be on first Pauli theory, Reinhard-Schwinger, and supergravity theories. These recent efforts have been done in collaboration with Oscar Fuentealba, Mark, Sucheta Mahunder, Turmoli, and also Cedric-Trossat in this year, 2020. So let's start with electromagnetism. Well, an overview is that we will impose some boundary conditions. This boundary condition will have to be modified by some parity condition in order to kill some problems in the finiteness of the symplectic form. So the kinetic term has some logarithmic divergences that has to be cured by imposing some parity condition on the leading functions. And then we will have to check the invariance of the symplectic structure. And then we will have a problem because the boosts are not canonical generator. That can be cured by adding an extra degree of freedom. I will show how. Then I will show the full action with this extra boundary degree of freedom. And finally, I will show the asymptotic symmetry algebra. I have to mention that all this talk, most of the talk, is based on the papers by Mark Genot and Cedric-Trossat. So let's start with the case of electromagnetism. Well, here you have the reference. I hope this is. So we can start with the Hamiltonian action for electromagnetism. What we have here is the vector potential, its conjugate momentum. We have some Lagrange multiplier and the constraint. We also have to consider, as usual, we have to consider this extra boundary term, which will ensure the well-defined action principle. Now we can impose the following decay for the vector potential and conjugate momentum, which is given by this expression here, where these functions, these bar functions, depends only on the function of the two spheres, depends only on the angles. As I mentioned, this condition will be constrained in order to guarantee the finiteness of the symplectic structure. This is going to be in the next slide. These boundary conditions are invariant under this gauge transformation with this parameter that goes in this way, goes linear in the expansion, an asymptotic expansion. This generator, the generator of the gauge symmetry, so the generator, generator of the gauge symmetries is given by this expression here, where on the constraint surface is just given by this expression here, this surface term. And it's not difficult to show that the electric charge is given by epsilon equal to 1, which is, as we will see in the next slides, is an improper gauge transformation. So we want the asymptotic condition to be invariant under Poincaré transformation, at least under Poincaré transformation. And we know that the general deformation of constant time hypersurface can be parameterized by the normal and tangential component, that's chi and chi. And in particular, for a general Poincaré transformation, we have this expression here, where these bi's are the Lorentz boosts, bij are the spatial rotations, and we have the standard rotation A perp and AI. We also know that the field transforms this way, where we have added some gauge transformation that this is going to be useful in the next slide. So we have Poincaré transformation, how the field transform. We're checking the variance of the asymptotic condition under Poincaré transformations. Let me move to spherical coordinate just for convenience. Here, this bar function only depends on the coordinates of the two spheres. We have split it there. So we have some arc component and some angular components. Now this field transform under Poincaré transformation in this way, where this gamma bar AB is the metric on the two sphere, and this dA is the covariant derivative on the two sphere. So nothing new. And here, so the asymptotic conditions are invariant provided this precise form of the parameters, where this B and YA are the homogeneous Lorentz transformation, and T and W are the usual translations. If we impose, so we have the parameters, well, we have to consider the Killian equations, which are the one in this line here. And if we solve the Killian equation, we will see that the B and YA are odd under parity, where parity is defined this antipodal map, where theta, psi, which are the angles, and R goes in this way. So this is the definition of parity in spherical coordinates. This is going to be important. So there are some interesting feature of this transformation that is the one that there is no mixing between radial and angular components. So this means that we can choose the parity of we can choose the different parity for the radial and angular component. That is going to be useful at some point. So now we will have to check the finiteness of the symplectic form. This means that we would like to have an action which is finite, so there are no divergences. But if we check, first of all, the kinetic term, we will quickly see that there is a logarithmic divergence here. There is a 1 over R here. This means that in order to have a finite, so in order to cure this logarithmic divergence, we will have to impose some condition on these functions. These conditions are going to be the parity conditions. Again, this is the specific form in the spherical coordinates. So we're going to impose some conditions, some parity conditions on the radial components. In this case, we're saying that the R component of the electric field is odd under parity and pi is even under parity. This is in accordance with there are no problems with the usual solutions such as the Coulomb field in a moving frame. These parity conditions is gauge invariant. We can check that from the previous transformations. And since pi r is now odd, sorry, even under parity, only the even part of the parameter is going to generate an improper gauge transformation. So the odd part is going to be odd. That means that this is 0. So only the even part of epsilon will generate something, will generate improper gauge transformations.
So,
now we have.
So excuse me, can I ask you a very naive question?
Yes.
So this kind of parity condition is the same as the matching condition given by Strominger on the antipodal point.
It's related, yes. I'm not going to talk about that, but yes, at the end of the day, it's related to that matching condition. But in that case, you have to, well, I will say something about that at the very end of the talk, but in few words, you have to go to a different, to hyperbolic coordinates. And then there is a prescription in order to relay the information on non-infinity and spatial infinity. And at least for the case of electromagnetism, if I remember well, yes, there is a relationship between the matching condition and the parity conditions. But
Okay, thank you.
yeah,
Okay.
yeah, but it's related. You can go to the paper if you want, at the very end of the paper. And there is a very precise
I got it.
Thank you.
Okay, thank you.
So we have to impose now some boundary conditions, some parity condition on the angular components. And this is the different thing that we have. There is a freedom to consider some twisted parity condition of the form of a gauge transformation. So this is a clear form of a gauge transformation on the angular part. In order to kill this logarithmic divergence, this psi should be odd under parity, and we also have to impose this extra condition on pi. This is compatible with the usual solution, so this is okay. It's gauge invariant and everything, so it's permitted. So now, as I mentioned, if we consider all this information in yellow, this parity condition plus the asymptotic conditions, this is equal to 0. So we got rid of the logarithmic divergence. So let's go to the next step, which is to check the invariance of the symplectic structure. So we can define, this is the usual thing to do. We can define the symplectic structure, which can be inferred from the kinetic term. Here's just a comment that this is the exterior derivative on phase space. Now we will see that there are some. We'll find some subtleties which come from boundary terms, which are usually neglected. So we have some boundary conditions, boundary terms, and these boundary terms are usually 0. There's no problem. But since we are dealing with different stuff, we are going to have some problems. Just remember that the transformation defined by the vector field x is canonical if respect this equation here. We can evaluate for Lorentz boost, so we can put the chi equal to Br in this equation here and use the transformation laws and everything, and we will get this term here, which is a boundary term. And since now this AB has an even and an odd part, this is different to 0. So this equation is not kept. That means that we have to do something in order to accommodate Lorentz boost. So the only problem comes from the Lorentz boost. The rest of the Poincaré transformation, it's okay. So the problem can be solved by adding a surface degree of freedom. Well, we have added this new field psi, which is odd. In this case, the even part is going to be 0. And we have to impose that this field transforms in this way under boost. We also have to modify the transformation law of AI in this way by a gauge transformation. And also we can define some psi field in the bulk, which matches at infinity in this way. So psi goes 1 over r times psi bar. So if we consider this field plus this transformation law, we will cure the problem. So this means that this term will not be there. We have modified the symplectic structure by adding an extra term, and this extra term is going to kill this problematic term here. So now, and it's important to say that the boosts are now canonical transformation. So the problem was cured by this extra degree of freedom psi. So now we can consider that this is the complete action. Now we have some extra degree of freedom, extra degree of field. This is the kinetic term that is a dot here. But now we can extend this surface degree of freedom to the bulk by considering some extra constraint by psi and its Lagrange multiplier. And in order to kill any problematic term here, some logarithmic divergence, we have to impose that the fall of the fields are of this form. We can check that the action is invariant under arbitrary shifts parameterized by mu. So we have this extra transformation law for psi. And now the generator is given by this full expression here. Again, this is on the constraint surface. We will have only this part that this is going to be the charge. Again, since pi r and ar has they both have different definite parity, only the even part of epsilon and the odd part of epsilon are going to be improper gauge transformation. But it's important to comment that this combination will form the full angle dependent U-Wall transformation at non-infinity. This is very important because you see we usually have epsilon, only epsilon. Now we had to add an extra degree of freedom. The degree of freedom has some parameter which is has symmetry. The symmetry is parameterized by this parameter mu, and both of them are going to generate the full dependent U1 transformation at null infinity. That analysis can be done in, as I mentioned, in hyperbolic coordinates and everything. So I will not have time to say something about that, but this is the prescription. So finally, since now Poincaré are canonical transformations, everything is okay. We have this generator P, which is defined this way with this expression plus this extra boundary term here, surface term, sorry, with some extra pieces associated to this psi field. Interestingly, the algebra of the generator is given by this expression here, which is just the semi-direct sum of the Poincaré algebra, and the abelian algebra parameterized by mu bar and epsilon bar. So some angle-dependent U1 transformation. This is abelian. There is nothing on the right-hand side of this bracket. And this is how the parameters are predefined. So the asymptotic symmetry algebra is a semi-direct sum of Poincaré algebra and the abelian algebra. And of course, this is an angle-dependent U1 transformation. So this is an infinite dimensional algebra. It's Poincaré algebra plus an infinite dimensional algebra. So this is the story of electromagnetism. Let me move to gravity. I think I do not have much time. So you can find this procedure or this analysis in this paper by Mark and Cedric. So in the case of gravity, again, we will start with the Hamiltonian action for pure gravity. We have, again, the conjugate momentum, the spatial metrics. We have the lapse of the shift, the Hamiltonian constraint and the momentum constraint, and we have this extra surface term in order to have a well-defined action principle. This is the usual stuff. We can consider this follow for the metric and the conjugate momentum. This is the more naive way to pose some follow on the fields, where this bar, h bar, and pi bar depends only on the angles. With these asymptotic conditions, with this follow-up, we can go directly to the kinetic term. And we will see that directly that there is we consider this follow-up, we will see that there is a logarithmic divergence, but this logarithmic divergence can be cured by considering the following parity conditions. So the metric is, the hij is odd, sorry, is even, and the pi is odd. This is the solution. This is the solution that you can find in the paper by Reguet-Edelman. I missed the reference here. Yeah? But the problem with this parity condition is that if you want to relax, sorry, this parity condition has to be relaxed in order to reach a coordinate system where parity holds. We might have to perform an improper gauge transformation, and such gauge fixing is not permissible. So we have to consider some improper gauge transformation, and that's the way that this problem can be solved. I will show you this in the next slide. So this is not the end of the story. So now we can consider some parity condition involving a twist given by an improper gauge transformation of the form of an diffeomorphism. So we have this extra piece for G and this extra piece for pi, which are linearized diffeomorphism. Here, this theta I and B are even and of order 1. This is compatible with any solution of gravity, such as, for example, the tap knot solution. And of course, we have some extra pieces in the asymptotic conditions with a definite, this twisted parity conditions. And this, of course, is going to complicate the charges, asymptotic structure, and everything. Nicely, we can solve these problems by considering, so for example, the divergences of the symplectic term and the Hamiltonian, as well as some problem with the boost, can be solved by asking the constraint to fulfill up to order r to the -5. So we have to impose a constraint up to certain order, but this is going to solve the problem. And now, and this is interesting because if you remember, in the case of electromagnetism, we had to add an extra degree of freedom, boundary degree of freedom, in order to cure a problem with the boost generator. So here we will have the same problem, but this problem can be solved by asking the mixed radial angular component to be 0. So we do not have to add an extra field, but just we have to modify a little bit the asymptotic condition. So we have to kill this the leading term in the r theta and r phi components, and that's it. So there is no need to add an extra degree of freedom, but we have to modify a little bit the asymptotic condition. But of course, this is compatible with everything, with gauge, symmetry, with the solution that are known in gravity and everything. We have to check that these asymptotic conditions are invariant under, at least under Poincaré transformations. We know that this transformation can be parameterized by this chi and chi I, and the field will transform in this way. Sorry. Here's the derivative. This is the usual formulation that you can find in the paper of Regate Deltenboim, for example. And so the asymptotic condition will be invariant if we consider this follow for the parameters, where now B are the boosts, YA are the spatial rotation, T and W are functional of the spheres. So these functions are completely arbitrary, are functional on the spheres. Here we have to modify a little bit the transformation by adding this couple of functions, CV and CVA. The CV is there in order to have a well-defined generator, and CAV is there in order to maintain HRA equal to 0. So this is just is in order to cure some problems, but everything is consistent. Then this is the usual stuff in GR. You have the generator of the transformation, which is given by this expression here, where this boundary term can be determined by integrating this term here. Now, if we consider our asymptotic conditions, so this means the fall-off plus the parity conditions, we can prove that this generator is finite, integrable, and canonical. So everything is perfect. There are no problems. And we can move to the algebra. So we have this generator P, and the algebra. This generator is going to be the VMS4 algebra, but in an unfamiliar parametrization. So this is a parametrization. But anyway, it's a VMS4 algebra. Interestingly, and similarly to electromagnetism, the odd part of W and the even part of T will combine to yield the arbitrary function that parameterizes super translation in the null infinity parametrization. So we need both. So in electromagnetism, we had mu and epsilon, and now we have W and T. And both, and the odd part of W and even part of T, will combine in order to parameterize the super translation at null infinity. Again, that story can be get from this hyperbolic story. So you have to go to hyperbolic coordinates and everything. But it's a very nice feature.
So Javier,
yes,
you have 5 minutes left.
Yes, no, it's okay. I'm almost done.
Thanks.
So this is the story, and just some ending remarks. So Mark and Cedric did the same for electromagnetism in higher dimensions. In that case, there is no need to impose parity conditions in dimension higher than 4. They also had to add some extra boundary degree of freedom, and the solution is quite similar to the case of 4 dimensions. You have Poincaré plus some direct sum of 2 independent U1 transformations in this case. They also did for Einstein-Maxwell. And in that case, you will get the semi-direct sum of VMS4 algebra with the angle-dependent U1 transformations. Well, I already mentioned this, but there are some comments on null infinity that you can, at least for electromagnetism, you can go to hyperbolic slices and solve the equation of motion in hyperbolic coordinates, and you can extract some nice information about the connection between null infinity and spatial infinity. In this paper by Campiglia, they show that there is for electromagnetism, there is an additional boundary degree of freedom, so the same that Mark and Cedric found. And in this formulation, so in this hyperbolic formulation, hyperbolic coordinates, it's possible to prove that mu and epsilon combine to form the full angle dependent U1 transformation at non-infinity. And well, as I mentioned at the very beginning of the talk, the idea of this talk was to give some context for the next talk. So the next talk will be given by Sucheta, and she's going to talk about the Fields-Pauli theory. So just linearized gravity. There are some interesting features there. Oscar is going to talk about, I think tomorrow, about the Ranita-Schwinger. So we move to speed 3/2. And Turmoli is going to talk about supergravity theory in 4 dimensions, everything in 4 dimensions. So that's it.
Thanks very much. Yeah. Okay, we are running a little bit late, but okay, we have, so Andrea has a question. You can unmute yourself and ask a question. Thanks.
Yeah, I was wondering, what is the story for superrotations of diffuse tools at spatial infinity?
Yes, well, Mark and Cedric, and well, we were also trying to get some super translation, but it seems that it's not possible. Yes, so super translation does not.
Superrotation, you mean?
Super rotation, sorry, do not appear, but it's still a work in progress. So I think that they didn't find the super rotation. We have been trying to get them for a while, but we didn't success. So it's not discarded. So it's possible to have super rotation, but for the moment it's not possible. We don't know how to do it. That's
By not possible, you mean that there is no well-defined charge that you can get, or?
Yes, it seems that we could have some escape from that by considering. So remember that we had to impose that HRH, so the mix component, the mix R theta and R phi was taken to be 0 because of some problem with the boost generator. So one possibility will be to have that different to 0 and see what happens. But again, the boost will be not very well generated. So it seems that the super rotation could come from there, but boost is not is spoiled by that condition. So we still don't know how to get super rotation. Maybe they are not there in this case, but as far as I know, there is no way to get super rotations for the moment. I have to say it's not discarded. Yes, thank you.
Okay, so I think Ali has a question. You can unmute yourself and go ahead.
Hi.
Hi.
Thanks for the nice talk. So have you compared your boundary conditions with those of Christodoulou and Kleinerman? Because to get these BMS symmetries, you need some like 1/r piece in GIJ. But I mean, if you evolve this initial data set to not infinity, then you might destroy the asymptotic behavior at not infinity. So in their case, they consider, I guess, a more strong boundary condition. So do you have any comment about that?
No, actually, no. I'm not. No, I have nothing to say about that. But what I know is that there are some problems with for example, in electromagnetism. If I remember well, we will discuss later. But I think there are some subtleties about that. But I'm not sure what to say about your precise question. But we can discuss later if you want. But
okay.
No, sorry for that.
So okay, maybe we'll have a last question from Mark before turning to the last talk of the morning. So, yes.
Well, in fact, it's not really a question. I wanted to comment on the previous question. I think that this comment shows that maybe the existence of a nice null infinity is something that can be problematical. And actually, that was one motivation for studying symmetries at spatial infinity, because you see, it's a very difficult question to know which initial data will lead to null infinity that you like. But if you work with initial data and see there that there is a symmetry, I think that puts the symmetry on a stronger footing. Now, it's true that super rotations have not been exhibited yet, and this is related to the question, to a point that was raised by Daniel in his talk. It's always tricky to put boundary conditions because that might involve improper gauge fixing. So the question is, maybe one can enlarge the boundary conditions to see to the super rotations, but it's true that this has not been done yet. Okay, that's it.
So can I just ask a follow-up?
Yes.
So what has been tried is only relaxing the condition on the angular radial component, not on the angular components.
Well, that's one thing that has been tried. Other things have been tried, but with less, I mean, things diverge very quickly or are non-integrable. So some ideas have been tried. Also, we have tried to exhibit what people call logarithmic super translations, and it goes to some extent, but then we face some difficulties that might perhaps be solvable, but we have not found a way to solve that yet.
But you try to relax to allow for change of the leading metric, like the what would be the analog at null infinity by relaxing the condition that the leading angular components have to be unchanged. Yeah, because the diffs2 do change the metric at leading order. And have you looked at the equivalent at I0?
Yeah, it's difficult to directly relate null infinity with spatial infinity, in particular because of the comment that was made on the Christodoulou et al. Integration, that we know that a smooth behavior at spatial infinity does not imply necessarily a smooth behavior at null infinity, etc. So it's tricky to relate, but of course one can, let's say, without relating, get inspiration, and indeed you can try to relax the 1/r behavior, but that's to do it while keeping charges integrable and finite. If you insist on that, it's rather, well, we have not found a way so far.
Thanks.
Okay. Okay, so I think we can thank Javier again for the really nice talk. We can clap and we can. Now we will welcome Sucheta for the last talk of this morning. Hi, Sucheta.
Hello, can you hear me?
Yes. You can share your screen.
Share my screen.